Well, welcome to week 2 in meteorology, geography 212. What we're going to talk about in this section of the course is some of the general characteristics of our atmosphere, specifically the origin of the atmosphere, its past and current composition, and its structure. So, just a few things to talk about here. First of all, our atmosphere is composed of gases and suspended particles. All right. Now, most people are aware it's composed of gases, but it also turns out that these suspended particles, which we also refer to as aerosols, are extremely important, and that'll come into play in the future when we talk about things like cloud development and precipitation. Half of the mass of the atmosphere is found within the first 18,000 feet in elevation above sea level from Earth's surface. And 99% of the mass of the atmosphere is below 20 miles. So really, the atmosphere hugs pretty closely to Earth's surface. Now, in terms of the evolution of the atmosphere, our atmosphere is far different today than it was early on. I'm just going to divide this up into two phases, and the first phase is going to be what I refer to as the primeval phase, which would have begun at the beginning of the age of Earth, which is approximately 4.5 billion years old. At the time, 4.5 billion years ago, the atmosphere we believe was primarily made up of hydrogen and helium, but we did have some ammonia and methane. And then, as early on in Earth's history, we had a lot of volcanic eruptions. Volcanic eruptions put out what we call outgassing. The two primary things that volcanoes put out then and today is CO2, carbon dioxide, and H2O gas, water vapor. So you can see that early on then, as volcanic eruptions continued, we started already seeing a change in the atmosphere as CO2 and water vapor is being put into the atmosphere. Now, as Earth started cooling after 4 billion years, this water vapor, H2O gas, started condensing into liquid water in precipitation in the form of rain and snowfall. And that is what the primary hypothesis is how our oceans got there, is from this condensation of water vapor. So in other words, rainfall filled up the ocean basins. Now, another idea today that's come into play recently is that we also think that oceans were formed by collisions with comets, because we've observed today that comets are largely frozen water or ice. Then, after we got a lot of carbon dioxide into the atmosphere, photosynthesis by marine life and then land life started extracting the carbon dioxide out of the atmosphere. They would split the carbon off to form leaves, stems, that sort of thing, but they would return the oxygen back to the atmosphere. So now we have a big change starting to take place where the CO2 is being replaced by oxygen. Then finally, at the end of the primeval phase, we see a lot of this oxygen working its way up into the lower stratosphere, combining with another single oxygen to form O3. And this O3 then is called ozone. And this was essential for life on land to develop, because what ozone does, it absorbs most of the ultraviolet spectrum of the sun, and ultraviolet light will kill life. So once we got the ozone layer formed, we now have protection for both land plants and land animals to come out of the ocean and start forming on land. We start seeing this happen about 400 million years ago. So, skipping to today, the evolution of the atmosphere, what does our modern phase look like? Well, you can see the list there, that nitrogen is by far the biggest constituent at approximately 78%. And then we have oxygen at 21%, argon 0.9%, carbon dioxide at approximately 0.04%, and that's increasing. H2O gas varies from place to place. And then aerosols, these are the solid particles that I was talking about. They remain buoyant in the atmosphere, floating up there. And there are things like volcanic ash, black carbon, for example, from the burning of fossil fuels, salt, dust, pollen. It really depends what part of the world you're in as to which of those aerosols are going to dominate in the atmosphere. Now, for example, here in the U.S. Southwest, as you might imagine, dust makes up the primary constituents of aerosols here. Now, if you take a look in your second chapter too, it's going to talk a little bit about, how do we know all this? How do we go about gaining information in sciences, and meteorology is certainly a science. And it's probably important to know a little bit about the scientific method. So I just want to spend a few minutes talking about it. In my mind, the scientific method starts completely first with observations. We observe things. For example, we observe year after year after year what time the sun sets, what time the sun rises at any particular latitude and longitude. And once we see that this sun will repeat that over and over, we can then go to step 2, which is proposing a hypothesis. A hypothesis is a statement based on observations. In other words, you're going to say, I do believe that the sun's going to rise at X time, at X latitude, every year, that sort of thing. So we're going to go out and test that hypothesis. That's number 3. In other words, test it over and over under a wide variety of conditions. Once we test that hypothesis and we see that it tests out accurately over time after time after time, we can then call it a theory. Sometimes these theories are called laws. So laws and theories, when you hear that, they are proven. A lot of people misuse the term theory and goes, I have this theory. No, you don't. You have a hypothesis. A theory is something that is tested out and we know it as true. Well, not all theories are going to end up. Some of these theories may fall by the wayside, but at least with this in the scientific method then, theories and laws are something that we accept as truth, as scientific truth. So then what do we do with theories and laws? Well, in science, we use them to explain and or predict phenomena. And I put an example in here we'll talk about later in the course, that the polar front theory explains how extratropical cyclones form. All right. Also in chapter 2, there's a bit on what we call monitoring the weather. How do we take observations, basically? Well, we'll talk about that in a minute, but in going back in terms of the longevity, at least in the United States, of monitoring the weather, we do have long-term instrumental records going back to 1731 in Philadelphia, 1738 in Charleston, South Carolina, 1753 in Cambridge, Massachusetts, and then out of New Haven, Connecticut, we have a continuous record of weather since 1781. Now, another piece of information is that the National Weather Service, this is a federal government operation under the National Oceanic and Atmospheric Agency, or NOAA, they were organized in 1965. Today, they have 123 offices where they put out weather forecasts, and we have 2 in Arizona. One's located in Phoenix, and the other one's in Belmont, which is about 15 miles west of Flagstaff, Arizona. Now, I want to mention something else about the National Weather Service. The National Weather Service is a federal government organization, and they are tasked with not just forecasting the weather, but also collecting weather data. So they're the ones that are collecting weather data out of the various types of weather stations that we have here in the United States. Many, many other agencies will use this weather information to provide their own forecasts, and I'm sure some of you have heard of some of these other agencies like the Weather Channel, like AccuWeather, Weather Underground, all of those agencies who generally rely on the National Weather Service observations to make their forecasts. All right, I'm going to take a look at, we're talking about the structure of the atmosphere, a couple of things we want to see here. Number 1, you can see in this chart, the atmosphere is divided up into 4 sections. If we start at the Earth's surface up to, just a little bit over maybe 8 or 9 miles, and it varies, we have the troposphere. All right, above that, we have the stratosphere. Above the stratosphere, we have the mesosphere. And then finally, at the very top of the atmosphere, very thin part of the atmosphere, we have the thermosphere. Now, the dividing parts of these 3 layers are all pauses of one sort or another. In other words, the division between the troposphere and the stratosphere is called the tropopause. The division between the stratosphere and the mesosphere is called the stratopause, and the division between the mesosphere and the thermosphere is a mesopause. Now, there's some interesting things going on here. This is the atmospheric temperature from Earth's surface as we ascend upward. Now, if you take a look starting at the troposphere and down at ground level, Earth's surface, What that chart's showing you is that the temperature steadily declines as we ascend through the troposphere. Now, there's a couple of reasons this takes place. Number one, the atmosphere predominantly is heated by the ground surface. In other words, short-wave solar radiation from the sun penetrates our atmosphere, and the atmosphere doesn't absorb too much of it. Most of that short-wave solar radiation is absorbed by the land. The land heats up and puts out what we call long-wave radiation. That's projected upward, and our atmosphere is very good at absorbing long-wave radiation, particularly, of course, the greenhouse gases like carbon dioxide, water vapor, and methane. Anyhow, so as you can see, the further you go up from Earth's surface, the further away from that source of heat you're getting, so the temperature cools off. But another reason the temperature cools off as we ascend in the atmosphere is because the atmosphere is getting thinner. That means the molecules are further apart, and as the molecules get further apart, they're going to cool off. All right, then you can see we go through the tropopause and enter the stratosphere. And you can see that the temperature stops falling and actually starts increasing as we move up in the atmosphere. And that seems not to be accurate when we take a look at what happens in the troposphere. But what's going on in the stratosphere to make the air warm up is that this is where the ozone layer exists. Remember, ozone is O3, 3 oxygen molecules bonded together. Now, one of the things that ozone will do is it will absorb ultraviolet radiation. The spectrum of sunlight that's ultraviolet, which is very short-wave radiation, is mostly absorbed by the ozone. When the ozone absorbs the ultraviolet light, it heats up. So it heats the surrounding air. And that's why we see a temperature increase in the stratosphere. Okay, then we enter the mesosphere, and the temperature is going to continue to drop, as you can see, just like we would expect. And then we get into the thermosphere. The strange phenomenon of a temperature increase is really not much to, I largely disregard the thermosphere because there's so few atmospheric molecules there. They're so far apart, it's almost meaningless. So we're not really going to talk much about the thermosphere. We won't talk about it at all. As a matter of fact, the only real important zone that we're looking at in terms of meteorology is the troposphere. So going back down to the troposphere, almost all the weather that occurs in the planet occurs within the troposphere. Now, it's true sometimes the tops of cumulonimbus clouds can poke into the stratosphere, but that's rare. All right. So there you go. There's your 4 sections of Earth's atmosphere, and this particular graphic is taking a look at what the temperature does as we ascend through these 4 divisions. Now, what you're looking at here is that's Earth there in the center, that little small piece in the center. And what it's showing is that we have something called a magnetosphere that surrounds Earth. We've got the North Magnetic Pole and the South Magnetic Pole. And those 2 locations allow what we call solar wind from the sun to enter. All the other areas of Earth, as you can see, are protected by this magnetosphere. Now, what is solar wind? All right, the sun is extremely hot. The surface of the sun is approximately 9,000 degrees Fahrenheit, about 6,000 degrees Celsius. At that high heat, the sun's heat strips electrons off of hydrogen and helium and shoots those electrons out into space away from the sun. So there's charged particles. You can just refer to them as charged particles. So these charged particles are streaming toward Earth. But because of Earth's magnetic field, creating this magnetosphere, most of these electrons or charged particles are deflected away from the planet, with the exception, of course, of the North Magnetic Pole and the South Magnetic Pole, where they're drawn in. So being drawn into North Magnetic Pole, for example, these electrons will come streaming down into the atmosphere and down into the stratosphere and even into the troposphere. And what they do is these electrons will excite atoms of oxygen, nitrogen, and other elements in the atmosphere and cause them to give off photons of light. And these, of course, are called the northern lights in the northern hemisphere. So Why this is important is that if the Earth did not have a magnetosphere, all of these electrons or charged particles would come streaming into Earth. And what they'll do is they can knock out our electrical grid, they can knock out our communication systems, between aircraft and ground or anywhere. So it's extremely important. It's a good thing that we do have this magnetosphere that protects us for the most part from what we call solar wind or these charged particles that are emitted by the sun. Now, when these charged particles do enter the atmosphere, as I said, it will excite the atoms of oxygen and nitrogen and cause them to release photons of light. And that's what you're seeing here in this photograph taken up in northern British Columbia. Now, there's a wonderful website called Space Weather that NOAA puts out. And we have these polar orbiting satellites that can show us exactly where these electrons or charged particles are interacting with our atmosphere. It's called the auroral oval. And this is just a screenshot from taken a couple of years ago, actually several years ago, as you can see. But what it shows you is if you take a look at this, and we can get these up to the minute from spaceweather.com, what you can see is where you would be likely to see the northern lights. And in this particular example here, you can see that in northern Canada and northern Alaska, and then northern Scandinavia and northern Russia, you would be seeing the northern lights. Now, this particular site, spaceweather.com, as I was mentioning, it's a very interesting site. There's an awful lot of information. So here we are, basically live today. You can take a look. If I scroll down here, where we do find this auroral oval, and I see that they don't have it on the front page these days. Let's see. You may have changed it a bit. Oh, they've changed it. Yeah, right here. So here's our auroral oval for today. You can see that there's not really a lot showing up today. Probability of visible aurora is, it's getting good when you get into yellow and red. I don't really see a lot of that. You see there's less than about a 50% chance of seeing it up there, even in the far north. So not a lot going on today with the auroral oval. All right, but there's a lot of other really good information on spaceweather.com. If you're interested, it gives us things like here. This will give you the amount of solar wind that's currently coming across. We have, by the way, how do we measure that? We have a satellite that sits outside the magnetosphere between the sun and Earth that gives us a good indication of how much of this solar wind is approaching us. Many other items on here you might be interested in regarding astronomy and other types of space weather. One in particular is this one, the near-Earth asteroids. We're not going to really talk much about those in this course, but it's nevertheless an interesting thing. So they're saying as of today, there are 1,703 potentially hazardous asteroids. In other words, these are asteroids that have relatively near-Earth orbits. And the way this works is you can see that, these are the dates when we're going to get a close flyby. Over here, the miss distance is measured in lunar distances. What a lunar distance is it's simply the distance between Earth and the moon. So for example, on May 14th, we had a 36 meter in diameter asteroid flyby at a distance 5.6 times the distance from Earth to the moon. So that wasn't real close. 1.6 is getting a little closer. If you look at this chart, sometimes you'll see less than 1 lunar distance, which means some of these asteroids actually fly by between the Earth and the moon, and that's getting pretty close. All right, so anyway, that's a really interesting site to peruse and check out sometime. If you get the chance, spaceweather.com. All right, well, that's going to conclude Chapter 2 here. So take a look. Make sure you look over basic understandings and read the review in Chapter 2.